Hello, everyone. So in this chapter, we've predominantly been focusing on a cost minimization problem, where our goal is to find out how much of the inputs, capital and labor, should be demanded in order to produce a certain given level of output, Q naught. So the way we've done this is we've solved the cost minimization problem. We have that tangency condition where W over V equals RTS, the rate of technical substitution. And from there, we write one input in terms of the other, put it back into our production function. And from there, we do a lot of algebra to get our hands on KC and LC, the contingent demand functions for the two inputs. Now, in this video, we're actually going to learn of a quicker way of getting to the answer. There is still some bit of algebra involved, but we're going to learn a particular lemma which helps us get to the answer. And the material here should remind you of how we used Shephard's lemma in the consumer theory space when we were trying to get our compensated demand functions. So our XC and YC compensated demand functions depended on the prices and a target level of utility. So, and we were dealing with an expenditure minimization problem there. So the parallel here is that we're dealing with a cost minimization problem. And our KC and LC will depend on the input prices and a target level of output. So let's go ahead and see how that's done. Well, we're now going to derive our contingent demand functions for the inputs using Shephard's lemma. And the lemma tells us that a contingent demand function for any input, okay, is just the partial derivative of our total cost function with respect to that input's price. So if you recall in the consumer theory, what did we do with Shephard's lemma? Our compensated demand function just came from taking a derivative of the expenditure function with respect to the price of the good. And that was the case for both our goods of interest. And what are we going to do here in producer theory? So producer behavior with cost minimization, with cost min, KC is just going to be derivative of the cost function with respect to its price. LC is just going to be derivative of the cost function with respect to its price. So this result actually comes from the envelope theorem, which we went through, which we spoke about very briefly. And I'm not going to get into the details here, but I just want to draw your attention to the result that Shephard's lemma gives us. So from a cost minimization problem, when you apply the envelope theorem, the lemma tells you that when you take a derivative of C with respect to V, you get your contingent demand for capital. And similarly, when you take a derivative with respect to W for the cost function, you get your contingent demand for labor. So let's go ahead and try that out in a couple of different, in a few different reduction functions. So the first one, but before we go there, always important to remember that these contingent functions, demand functions are not a complete picture of input demand because here we are keeping the level of output fixed. In reality, output levels will also vary. So the producer will actually be trying to figure out how much of output to produce to maximize profits and how much of inputs to produce that level of output. Now we just simplified our problem by fixing this level of output. Now this is not the complete picture. So it's always important to keep that in mind. So let's look at the fixed proportions case. So this is the one where we solve it a little bit differently to find the cost function. We don't do a cost minimization as such because here the production happens at the vertex. So in that manner, we earlier identified the cost function as Q times V over alpha plus W over beta. And from here, it's a very simple process of computing derivatives to get to our contingent demand functions. AC is just going to be derivative of this with respect to V. So you get Q over alpha. LC is going to be Q over beta. And this was, so that's how we solve it in the fixed proportions case. Let's look at how it turns out in the Cobb-Douglas case. So once you have a cost function that is given to you for a general Cobb-Douglas function of the form K alpha L beta, from this function, we just have to take derivatives with respect to V and W. So to get Kc, I just have to differentiate C with respect to V. So if you notice, V has an alpha over alpha plus beta as the exponent. So I just put alpha over alpha plus beta. The other terms stay as they are. And I'm going to be left with a W term. And then I think I'll have a V to the power minus beta over alpha plus beta. So I'll let you work out the algebra, but this is the final answer that you get. And you can also similarly write down your labor demand function. And if you actually compare it with the Kc and Lc that we derived a few slides earlier, they're the same. And then the contingent demand for the CES case. So this is our cost function in the CES scenario. If we take derivatives with respect to V and W, we get our contingent demand functions. And based on different parameters that sigma and gamma take, you can characterize production functions, which could be one of the three cases we see very often: Cobb-Douglas, substitutes, or complements. You can also bring in different returns to scale based on the value of gamma. So just by plugging in some numbers here, if we choose to have gamma equals 1, and if we set the other levels of V, the price of capital, the price of labor, an output target, and a certain degree of substitutability, for these sets of numbers, we actually need 25.6 units of capital and 1.6 units of labor. So we're losing almost 16 times the amount of labor to produce a certain level of output here, just for numerical, just to show you an illustration. Now, we're just going to do one final addition here. We're going to use this Shephard's lemma in place of our elasticity of substitution. So if you recall, we came up with another measure of elasticity of substitution, which is just percentage change in K by L, given a percentage change in their prices. And we saw that this was actually only defined at the optimum when the cost minimization was happening. Now, if you were to think of this as Kc and Lc, we could just get Kc and Lc from the cost function itself. So if we just substitute the Shephard's lemma notation into this elasticity of substitution formula, elasticity at the minimum cost point can be rewritten in this manner, where Ci and Cj are actually just partial derivatives of your total cost function with respect to particular input price. So here, if xi is my input, Ci is just the derivative of cost function with respect to its price. Cj is just going to be derivative of the cost function with respect to the price of input j. So this is an even more convenient form because it's easier to get our hands on the cost function, and from there we can directly figure out what K and L are, or whatever the inputs are. And then we also know what the prices will be. So using this, we can very conveniently talk about elasticity of substitution. So that's it for this video, and we just have one final segment left. So I'll meet you in a different video. See you there.